Morning, everyone. So welcome back to QX01, Introduction to Quantum Information and Associated Technologies. So let's have a look at the program. So for today, we are going to finish part one of quantum algorithm. And then, so that will be for about an hour. And then there will be a second part, which is not going to be live on YouTube. It's going to be recorded and then put on YouTube later on. And that's going to be on the second part of the quantum cryptography a lecture that we had already from the University of Bristol. And this time it will be given by a colleague from a startup, British startup company called QX01. So that will be at 11. So for today, only 1 hour of on live YouTube. For the rest of the weeks, nothing is really quite confirmed yet. So there will be something next week. It might be on quantum sensors or not. We'll see that. Not quite sure yet. What's for sure, there will be nothing on that day because it's a day off. And then there will be a quantum algorithm part 2. Hopefully, that should happen on the 1st of June. And then a company, so for colleagues from the INRIA Institute, and then there should be the company Atos, who is going to present an introduction to the quantum learning machine experience. And then the last lecture will be given by me, and I will very briefly introduce quantum error corrections and wrap up with the different quantum technologies that there is out there, knowing that I already covered some of them during this series of lectures. Right. So for today, it's so let's finish quantum algorithm part 1. So what we covered last time, we covered well, very briefly introduction of algorithm, of classical algorithm. Then we moved on to talk about the different families of quantum algorithms, and we said there are a lot less of them as opposed to classical algorithm. And then we gave a specific example of hybrid classical quantum algorithm. And in fact, this is going to be covered again by the colleagues from the Atos company, who is going to mention this application as an example. As of today, so we will do, which we started last week, the example 1 of algorithm, which is the Deutsches algorithm, the first one. Then I will talk about the no cloning theorem. So this is something I guess I should have done before. I promised it, so I will do it. And you will see how simple it is, in fact, and how it is important how important it is for many applications, and one of them being quantum key distribution and quantum cryptography that will be covered by another colleague. And then something I added at this stage, so we'll see if I'll manage to cover everything today, which is what I call thoughts on the Schrodinger equation. It's to give some physics insight onto some of the aspects that we've seen so far, and in particular, how useful can be the Schrodinger equation for some quantum mechanical problems, but also for quantum technologies. And then this part of quantum algorithm will be done by with the Simons algorithm covered by colleagues from the INRIA Institute, and that will be on the 1st of June later on. Right, so, okay. So, Deutsches algorithm. So the Deutsch algorithm was discovered by this man, so David Deutsch, in 1985. And it's a very important algorithm because it's the first one that really showed on a concrete example that there is an advantage of using quantumness compared to classical algorithm and classical information. So it's a proof of concept. I mean, it's the first one. That's why it's important. but it's not particularly useful. But again, it's a proof of concept, and that led to other people to think that, well, perhaps we could actually do something useful, and that's what was done afterwards by this man also, the so-called Deutsches algorithm, and then the Simon, Grover, Shaw, and so on and so forth. Right, so what is the problem that we want to solve here? So the problem is, let's consider a binary function f. So it's a binary function, meaning that it can, so it's got a function that takes 0, 1 and bring it to 0, 1. All right? So for this function, there are 4 possibilities that can be split into 2 families. The first possibility is the so-called constant possibilities, which is both inputs, so whether I took x equals 0 or x equals 1, will give me 0. So f of x is 0 no matter what x is, whether it's 0 or 1. So it's mapped to 0. The second possibility is the same one, except that now it's mapped to 1. So if x is 0 or x is 1, f of x will be 1, no matter what. So this can be put up as the so-called constant family in the sense that these two possibilities, yes, are tell you that f0 equals f1 in both cases. Whether you map it to 0 or map it to 1, the output f of 0 is equal to f of 1. So we call it a constant, the constant case. The other two are different in the sense that the first one is that inputs after f are, outputs after f are unchanged. Or inputs or output, depends on how we say it. So in a sense that whatever x is, f of x is going to be x. So f of 0 gives you 0, and f of 1 gives you 1. So you just map it. You don't modify anything. And the other one is that the inputs are exchanged. So if you start with 0, you end up with 1, and if you start with 1, you end up with 0. So in both of these two possibilities, you can see that f of 0 is different than f of 1, right? As opposed to earlier, where f of 0 was equal to f of 1. So we will call these two cases the balanced case. And now the question you want to solve is find out whether the function f that you don't know about, I give you this function, I don't tell you what it is, I don't tell you which computation it does out of these 4, but I'd like you to tell me if this function is constant or balanced in the minimum number of steps. So, right, let's have a look at how you would do that. Well, in classical algorithm, you need 2 evaluations. Basically, you need to measure f of 0 and f of 1, and then just compare. If f of 0 equals f of 1, no matter what, then you're in the constant case, and f of 0 is different than f of 1, you're in the balanced case. You need to make 2 measurements, f of 0, f of 1, and compare them. So this is what this algorithm would do. If f of 0 equals 0, then if f of 1 equals 0, then print constant, otherwise print balance, and otherwise if f of 0 equals 0, then if f of 1 equals 0, then print balanced. That means you started from f of 0 equals 1. Otherwise, print constant. So that would be a classical algorithm, and you can see that you have to make 2 queries on your function in order to have the result. So what about the quantum case? Well, quantumly, as we will see, only one evaluation, one query is needed. Okay, not 2, but just 1. And here's the circuit of the Deutsches algorithm, so we will go through it. And in Deutsch algorithm, what you do is you start with 2 qubits, okay, Q0, Q1. You initialize them in some states, so 0 and 1. Then you make on each of them, you make a Hadamard gate, okay? And then you make a joint measurement between these two through a unitary matrix, so a 2-qubit gate, that we will call U of f. And what does this matrix represent? It represents the function f. One way of seeing it is this is something so we don't know what's inside because we don't know what the f function does, and that's precisely the point. We don't know, so we want to know. So that's why this can be seen in a way as a black box. And this black box has to be unitary, as we said before, like every quantum gate. So you need to be able to reverse it. And once you go through this black box that we're going to discuss, then what you do is on the first qubit, you apply a Hadamard gate again, and you measure. And this one here, you don't actually need it. You can just throw it in the bin. And here, so you make a measurement. I remind you that the double lines means that you have now a classical information. And in fact, as we will see, depending on the result you find, so you either find 0 or 1, then if you find 1 or 0, then it will tell you whether f is constant or f is balanced. And that's it. Just one result, 0, 1, tells you if f is constant or f is balanced. And that's it. Only one query. Okay. So how does this work? So let's, as we did before, how do we go from the quantum states, from the quantum circuit to the quantum states and back? So we're going to look at every wave function here at every stage and see what they look like. So the first one is the initial state, so psi 0 is 0, 1. Okay, so you start with 0, 1. And then you make a Hadamard gate on each of these qubits. So now we know what it does. It's basically we transform 0 into plus, we transform 1 into minus, where plus and minus can also be seen as the, so if we talk about photon polarization, the plus minus or the diagonal, anti-diagonal basis. So basically what you do now is you take 0 and you put it in a superposition state of 0 plus 1, and you take 1 and you put it in a superposition state of 0 minus 1. So if you do that, so you develop plus minus and you get this 4-term wave function. So you can show you got 1/2 because each of them gives you 1 square root of 2. So you will end up with 1/2. 1/2 of 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. Okay? And now you carry on. So now we go through this unitary function. So now we end up with another wave function, psi 2, which is the result of applying this unitary function U of f, which is a 2-qubit matrix, on psi 1. So U of f, as I said, like any quantum gates, has to be a unitary. So I remind you on definition of a unitary matrix. So U of f, I should put a hat really on it, is unitary if U dagger f UF equals identity. Okay. And so the only condition is that UF is unitary, and we don't know it. So we can, sometimes people talk about an oracle, because it's a black box, and all we can do is just interrogate this black box, this oracle, in order to know the answer. So that's another way of seeing this problem. So, okay, so we carry on. So what this unitary function looks like, well, you can show that this unitary function can do the following and be, and that way be works for any f function that goes from a 2-qubit 01, sorry, a 2-bit 01 to a 1-bit 01 to another 01. So for that, you take 2 qubits A and B, you send it into this function, and what this function does, this quantum gate does, is that it leaves A unchanged, and for B, it adds as an XOR sum, addition, the result f of A. Okay? So I remind you what the XOR sum does with sort of the truth table for 2 standard bits of information. So if you have A and B, A XOR B will give you 0, 0 gives 0, 0, 1 gives 1, 1, 0 gives 1, and 1, 1 gives 0. So it's a real sum in a sense that we covered that already, that A XOR B is a sum, but in a what we call Z over 2Z space with 0, 1 as a space only. So what it means is that 0 plus 0 is like the normal sum. So 0 plus 0 gives you 0. 0 plus 1 is like normal sum, gives you 1. 1 plus 0 is a normal sum, gives you 1. And 1 plus 1 should give you 2, but 2 in a Z over 2Z goes back to 0. So 2, but transform into 0. So in that sense, is a true sum, but on a 2-element space only. Anyway, you can just see it as a truth table with rules, and these are the rules. And so you can show that this quantum gate here, this unitary matrix, actually works for any function f out of the different possibilities that we gave in the first place. And one of the reasons is because precisely f is unitary. And for instance, if I apply uf twice, so if I do b plus if fa plus fa again, I come back to b. For this reason, that if I do so 0 plus 1, and then again plus 1, I go back to 0. So, okay, so now this psi2 wave function, or quantum state, after this unitary transformation, this unitary matrix UF, we'll be applying UF onto psi1. Now I've got 1/2 of UF 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. Okay, so let's do that. Oh. So that would be UF. It's of, so I'm going to take the 1/2 out, and I have 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. So what this does is that this transformation leaves the first one untouched, so 0, 0, 1, 1 will not be changed. And the second one is going to be this one plus plus the f of a, so the, where is it? Yeah, here. Plus the f of a, where a is the first qubit. So if I do that, so if I apply it to this one, so I've got the 1/2, so the 0 is untouched, and then for this one, it becomes f of 0, okay? Because what I did is I took b, in the equivalent here, I took b, which is 0, plus f of a, which is 0. So I've got 0 plus f of 0. I can write it, actually. Let's write it. 0 plus f of 0. That would be f0. Then for the second one, I have minus. I've got 0 again. And then I have 1 plus f of 0. Okay? As a, sorry, plus, like this, yeah. So that I don't know, because it depends on what f does. So I can't touch that. I have to leave it as it is. Then I've got the third term, which is plus, first one is left untouched. 1, and then I've got 0 plus f of 1. And this is going to be f of 1, because 0 plus anything gives me anything. And then I've got the fourth term, which is minus 1, and then 1 plus f of 1. And that again, like this one, I don't know what I'm going to have, because I don't know what does the f function do. Right. So now, it will depend on the f function. So now I can treat two cases. So either the constant case or the balanced case, once I found something to an eraser. Okay. So psi 2, if I rewrite it, is going to be 1/2 of 0 f of 0 minus 0, 1 XOR f0 plus 1 f of 1 minus 1 XOR f of 1. I just rewrote that here. So now I've got two cases to consider. Right? It's either balanced or constant. So let's two cases to consider. So constant, as in f of 0 equals f of 1, no matter what, or balanced, as in f of 0 would be different than f of 1. So let's do the first case. So the first case, so if f constant, then what I can do is I can replace one of those, say this one and this one, by f0. Okay? So that's what you have here. So here I just rewrote the same equation like I did here. And actually there is a mistake here. It should be f of 1. So let's write here. So if I do that, I've got psi 2 equals 1/2 of 0 f of 0 minus 0, 1 plus f of 0 plus XOR plus 1, and then I replace that by f0 because it's a constant, okay, and minus 1, and I replace that one also by f of 0. There we go. So what I can do is I can put 0 in factor here, and I can put, oh, sorry, wrong one. Wrong one. That's not the one. I can put f of 0 in factor here and here, so that I will obtain 0 plus 1. And I can put 1 plus or XOR f0 here and 1 XOR f of 0 there in factor, so that I will have 0 minus 0 plus 1. So let's do that. So I've got 1/2 of 0 plus 1 f of 0 minus 0 plus 1 of 1 XOR f of 0, and that's it. Okay. And now I can take 0 plus 1 here and here and take it out of the brackets and obtain. So and obtain 0 plus 1 brackets of f0 minus 1 plus f0. No, so there's no mistake there, actually. So if I go back to the slide, so now, so this is what I did. So I replaced f1 by f0, this expression. Then I factorize it, like I just did. And I end up with 1/2 of 0 plus 1, and then times a tensor product. Here is a tensor product. It's actually a tensor product of something that is f0 minus 1 XOR f0. But we will see that this we actually don't care, because this is the first qubit, so this one, and this is actually the second qubit. And like I said, so this second qubit has some function, some result that we don't know, because we don't know f, but actually we don't care, as we will see. We don't care because what matters is the first qubit, because the first qubit now is in a state 0 plus 1, and I can rewrite this state as being, with a square root of 2, the plus state. Okay? So what I did here, I said that, well, if f is constant, then psi 2 will look like 1 square root of plus, so for qubit A, so qubit 0, the first one, sorry, time or tensor product, the second one, which is something a bit complicated that we don't know, but we don't care, as we will see. Now, if I do the same trick for the balance case, so the balance case means that f of 0 is different than f of 1. So in this case, that means that whenever I have 1 XOR f0, like here, for instance, then this would be f of 1, because it's unbalanced. It's balanced, sorry. And whenever I have 1 XOR f of 1, then I would have f of 0. Okay, so in this case, I would have to obtain f of 0 because it's balanced. It has to be the opposite of what I have. So if I do that, I can replace the 1 XOR f0 and 1 XOR f1 in these expressions by f1 and f0. And then do the same trick in the sense that I will be able to factorize by this time 0 minus 1 times or tensor product f0 minus f1, which I don't know. But again, this is on the second qubit, and I don't actually care about this, because what matters is that the first qubit now can be transformed into a minus state. So here, minus being 0 minus 1 divided by square root of 2. So what I have now is that I took my 2 qubits, I went through this function f that I can model by what we saw before, by the XOR applied on the second qubit. And then what comes out is actually, for the first qubit, so what comes out is a 2 qubit state. For the Q1, the below one, it's some complicated function that depends on f that I don't know, but I don't actually care, because what matters is that the top one, the Q0 qubit, the top qubit, for this case, is either in the plus state or the minus state. The plus state is when we have the constant case, and the minus state is when we have the balance case. So it means that afterwards, if I apply again an Hadamard gate on this qubit, then I will go from plus minus back to 0, 1 and map it. So in other words, that means that when I have, in the first case, if f is constant, then psi 2 is plus tensor product this thing. So plus will be here. And for the balance case, the upper qubit will be in a minus state. So if I apply Hadamard, whatever that is, that means that the constant case plus will be transformed into 0, and the balance case with the minus state will be transformed into 1. And then I can just make a measurement and find out whether I have 0 or 1. And if I have 0 for psi 3, if I actually measured that psi 3 equals 0, then it means that I was in this case and that the function was constant. But if I measured 1, that means I was in this case, which is the case where f is balanced. And this qubit here, which is so when I make the measurement here, I project this qubit into either that or that, which I don't know, but actually don't care, because I already have my answer. I already know now that Q0, if Q0 at this point here, gives me 0, it's constant, gives me 1, it's balanced. So in one query, I have my answer. So by just using 2 qubits, one that I actually throw away and one that I measure, so by only one query on this function that I don't know about, as opposed to earlier where I needed 2 queries, then I have my answer. 0 gives me constant, 1 gives me balanced. Okay? So you can see here on this simple example, not so trivial to do actually, but simple, that there is an advantage in using quantum algorithm as opposed to classical algorithm. In one case, we needed 2 queries, and in this case, we need only 1 query. So, of course, it's an easy case, it's a small case, but if you remember, I mentioned that quantum power is 2 to the power of n, as opposed to n when you use classical algorithm. And here you have it, because, of course, here n equals 1. But the fact is that you go from 2 queries to 1 query. So you exponentially decrease the number of queries that you need. Of course, it's on a very simple case and not very useful, but again, that was the first example of the power of a quantum algorithm as opposed to a classical algorithm. And that led to more powerful ones that are actually useful. So that's what I wanted to say about the Deutsch algorithm, to give you a first example of an algorithm. Just a quick note on that, because it turns out that David Deutsch is actually a believer in the so-called many-world theory. So this theory is actually quite controversial. It's a possible theory of quantum mechanics. But I'll just give it to you anyway, because, well, you may have heard of it. So the many-world theory, just to give you, to tell you what it is. So this was developed by someone called Hugh Everett, who developed this so-called many-world theory of quantum mechanics. And what this tells you is that, so if I take again the example that we took some time ago of the Schrodinger's cat. So if you remember Schrodinger's cat in the box with this bottle of poison that could be broken or not, depending on the state of the radioactivity of a gas and so on and so forth. And Schrodinger's cat tells you that we arrive at this contradiction that the cat is either dead or is dead and alive at the same time. It's not either dead or alive. But when you actually open the box, then at some point you have to find whether the cat is dead or alive. It cannot be both at the same time. So the many-world theory tells you that yes, it can be both at the same time. It's just that the cases are in different universes. So in one universe, the cat is alive, and in another universe, the cat is dead. And you've got these parallel universes, these superposed universes all along that sort of live in parallel. So for instance, right now, we could be in a universe where I'm talking to you in front of you, but maybe in a parallel universe, I'm actually at my desk doing something else. In another one, I'm actually doing some shopping. Another one, I'm actually going to play football, although mind you, this is difficult these days, and so on and so forth. So all these possible universes are in parallel, except that the probability for me right now to be at my desk is almost, is 0, because I'm talking to you, and they are observable. There are people observing me, so my wave function has collapsed into this universe. So I'm in front of you right now, and I will remain it, hopefully, for the rest of this class. But the fact is, the many-world theory, so in a quantum case, again, I'm not a quantum object by definitions I gave before, but a qubit, a photon, an electron could be can be in a superposition state, and perhaps, according to this theory, could live in 2 different universes. So another example is recently in some movies where the exploration of parallel universes was taken into what happens if you have this split into different possibilities. So in this case, if I go back to the example of the Dutch algorithm, in one universe, the function is constant, in another universe, the function is balanced. Okay, and that's what David Deutsch would say, according to the many-world theory. Right. Okay. So before going on to some thoughts on Schrodinger equation, I just want to come back to a very important concept that I've mentioned a few times, but actually I haven't demonstrated, is what we call the no-cloning theorem. So there is a very powerful theorem that can be, as we will see here, be proven in very simple, in few lines, is the fact that quantum mechanics tells you that there is no box, no machine that can take a quantum state in and can spit out the quantum state and its copy, perfect clone at the same time. Okay, so you cannot come with psi and come out with twice psi. Okay, there is no such thing. So in quantum mechanics, or in quantum technology vocab, it means that there shouldn't be no operator that can clone a quantum state. Okay, so it's okay for Dolly, you know, the famous sheep that was cloned, but technically, Dolly's clone is actually a different animal altogether because they cannot be perfect clones. Quantum mechanics tells you that there is no such thing. So at our level, it's not a big issue, but on a quantum level is very important, and that actually is a proof, for instance, that can be used in quantum key distribution as a very secure way of communication. So how do we prove that? So how do we prove that there is no such machine? There are actually two proofs that can be, so two different ones. So I'll give you the two different ones. So the first case is by simply using the definition, sorry, the definition of an inner product, or the scalar product in this weird Hilbert space. So let's assume I have the quantum state I want to clone, so phi, and I make the tensor product of phi with a qubit, say, in state 0. And a cloning machine is an operation, so unitary transformation, or at least that's what we assume that there does exist, that will take that state and make a copy, a clone, a perfect copy of that state onto this one. So this machine would take this and transform it into this. All right? So ideally, this machine, this operator here, this matrix here, this 2-qubit matrix, will do the same for any quantum state. So if I use another one, psi of 0, this machine is going to clone psi and make a copy of it. And now what's interesting is to look at the inner product between these two. So let's have a look of phi, psi. Okay, so bracket, remember the bracket notation. So all right, so I'll do that. So I'll transform, so what I can do is I can put the tensor product of this bra with the qubit 0 and this ket with the qubit 0 as well. So I can transform that into that. Okay, so now I sort of split these two, okay, by putting parentheses, but it's actually an inner product. And then on the other side, I can do the same and write it like this. Okay, I can always do that. I can always tensor product to another qubit. And now here in the middle, I can put the operator identity. I can always do that. If you remember, when we have, for instance, the mean, the average, the mean value of an operator A, we squeeze it between a bra and a cat, well, here I can put the identity operator, and that would just gives me phi psi. That, by the way, is a very standard computing trick that is used in quantum mechanics in general, in quantum technologies in particular, and quantum information, in order to make things appear. And the thing that we want to make appear here is precisely this matrix, this unitary cloning machine UCL. Because presumably this UCL is unitary, like any quantum gates, and in this case, U dagger CL of UCL equals identity. So I can now replace identity by this, and I would have psi tensor product 0 of U dagger CL, and then UCL psi of 0. But this here is this transformation, right? So if I use colors, so this is precisely the transformation of cloning. And this part here is the adjoint operation, is the bra version, but it's the same thing, is that I apply the dagger operator to the 0 state, and that, or to 0 phi state, and that would be the exact same thing to go from here to there, but in the bra version. So this is in fact psi. Okay. So now I bring everything together. So yeah, there is something is missing here. Let's go to the next one. So now I bring everything together. So here's what I did here. Here I've got these two now. I've got psi cross psi and phi cross phi and psi cross psi. But this is, if I put these two together, I obtain the inner product, and then these two will then go together as well and give me the inner product as well. So what I have here is in fact the inner product squared. So what I find out here is that when I take this cloning machine and clone psi and phi, and when I do the inner product of phi and psi, then I end up with this inner product being equal to the inner product squared. Okay, well, that's allowed, except that in this case, if x squared equals x, then that means x equals 0 or 1. So it means that the scalar product between phi and psi has to be 0 or 1, and nothing else. But that is not true. I made no assumption whatsoever between phi and psi and phi. So there is no reason why the scalar product between the two will give me 0 or 1. If I take this one is 0 and this one is a plus state, for instance, I will not find 0 or 1. I will find 1 square root of 2. And that's just one example. So this is not true. Therefore, this is not true. So there is no operator UCL that can take this state and clone it to this one, or any state and clone it to another one. Because if I use the inner product, then I end up with a contradiction. And that is a proof So it's proof number 1. We will see next time proof number 2, because now time is running out. We will see proof number 2, which uses this time the linearity of quantum mechanics, but we will end up with the same sort of result, in the sense that we will end up in a contradiction, in this case showing that this state has to be equal to this state, no matter what A and B are, which is not true. And we will, again, come to the conclusion that there is no operator UCL that can clone any quantum state and make a copy of it. Therefore, in quantum mechanics, you cannot clone a quantum state. Okay. And this, as I said, is at the heart of quantum communication, in particular quantum key distribution, and that's what makes it secure, because not only it tells you cannot make perfect copies, but on top of it, some protocols, like the BB84 or any, in fact, quantum key distribution protocol, tells you that if you try to even to clone a quantum state, then you can be seen. So not only you cannot do it, and then if you try to do it, I can see that you try to do it. Okay. So that's how powerful that is for some applications. So with this, I will stop here for today, for the live version. So now there will be the second part of the quantum cryptography part. So this will be separate, and this the second video of the quantum cryptography part will be available on YouTube at a later stage, like the first one was. And with this, thank you, and I see you next week or the week after that for the next courses. Thank you for your attention.